Hello, so today I'm going to talk about a relatively new technique for sensing in the ocean over very large scales. And I'll give you an example of something about properties of sound in the ocean. Whoops, sorry. I don't know what I just did here. Okay, so here we are on the east coast of the United States, and you see some of the familiar states. There's Washington, New York, and here we're looking at the continental shelf, and water depths on the order of 100 meters or so on the edge of the shelf. Here I'm showing you from the center of the circle how long it would take travel to travel out and back. And that's 40-second to two-way travel time. So in 40 seconds, you effectively can image an area this size, which is about 60-kilometer diameter. You wait twice as long, 80 seconds, and you can image 120-kilometer diameter. And these are on the order of the size of the East Coast state of the United States. And essentially, that's what we did. We were out doing some survey work here on the continental shelf back in 2003 with a new type of sensing technology. We have a source ship here, a receiver ship here. The source is transmitting sound in the audible range, higher than my voice, about an octave higher than my voice, and receiving it here with an array of sensors. And what we're able to do is image everything in that whole area. And what we found here is a very, very large shoal of fish. I believe it's herring, and imaged from on the order of 15 to 20 kilometers away, and instantaneously sensing the structure and the internal structure of this very large shoal. And we were told this is the first time that's ever been done. This is about a 15 to 20 kilometer long shoal with a population on the order of 10 to 20 million fish. The next day, everything changes, and we see a very different scenario here, different groups of fish. I can show you a movie of this, and maybe it's a good time to do that now. Let's see. Actually, a little technical difficulty here. Maybe I shouldn't do that. Maybe I'll try to do it afterwards. I've got to get back to get back into, all right. Maybe I'll just keep on going like this. Okay. So, all right, so it's done it for me. Here we go. Okay, well, effectively what we've done, and if we have time to see the movie, what we've done is we make updates every 50 seconds or so and form a movie of the evolution of the shoal. And in the morning it was one consolidated shoal. Around midday it broke up into many different pieces, and we can see some of that here. We actually had a conventional survey ship going through and found very good correlation with the standard echogram. That's now range depth. This is range. This is east, and that's north. And I think one of the important things about this new method that we call OARS, Ocean Acoustic Waveguide Remote Sensing, and I'll explain a little bit why we say waveguide, is that you're sensing every pixel in the image at every time. And so when you make an update, you're then seeing every pixel at the next time, whereas with a conventional echo sounder, you actually have to form a synthetic image, and you're, in this case, looking downward and looking at all the depth points. You move to the next range, and then you collect all the depth points, and you synthetically make them. So we would call this a Lagrangian frame, where you're constructing a sort of time-space path through the shoal, whereas in this OARS approach, we're looking horizontally, but every time and every spatial location. Now, I think the analogy is you can think of the OARS as a sort of a movie of the entire environment, and every pixel in the movie screen is there. And as you evolve in time, you're able to see the whole scene unfold whereas with a conventional kind of survey, you effectively only have one pixel in the movie and you're moving through with that one pixel. It's very difficult, in fact impossible, to recreate the scene, and so you have too poor sampling to understand the dynamics of the populations over these very, very large scales. And this is something that this new technique is actually bringing. Another thing that it brings is you can take spatial spectra and you can look at the population distributions over spatial frequency, and we found that it follows a very nice power law structure, which means that there's an order, and the order is a fractal kind of order, and what it's saying is there's a self-similarity at very, very small scales and very, very large scales. If you look like in a snowflake, you would find the structures are very similar, small and large scales. Most of the energy being in the larger scales, and when there's a big shoal present or absence, it simply moves the power law structure up and down. So this is one of the advantages of having this synoptic type viewing ability. We also looked at the total population as a function of time, and population was changing as the shoal broke up. And you may ask yourself, well, what is happening to the population of the fish as it's going down? Well, what's happening is the fish are dispersing to the point where we can no longer sense them anymore. The brown stuff that you see in the background is actually returns that we get from the seafloor. And when the fish are too dispersed, we can no longer find them. And it's something on the order of one fish every 10 meters or so is the level where we stop being able to sense them. Okay, we've looked at a number of methods of looking at velocity flows of the fish, and we've recently published another method on doing that in IEEE, where you can actually take a sequence of these density images and turn it into a flow field that evolves with time. It's based on a fluid dynamical model for compressible fluid dynamics, and you can actually also determine the forcing functions that are driving the flow and what that would mean for a very large shoal, what it is that's causing the populations to merge or split apart or expand and contract. This is something that needs a biological basis, which we don't have. We only have a physical basis for what we're seeing, but the actual pressures and forces we've been able to quantify, and what they mean biologically still needs to be interpreted. Now I'd like to talk, we applied this method, the ORS method, again in 2006, and that was in the Gulf of Maine. The approach is really to use a vertical array of acoustic sources and send the sound out. It's sent out horizontally, almost like it's truly semicircular rings that are going out. If you put your finger in a pond and you see the rings traveling outward from your source, it's very similar to what's going on. The sound stays trapped in the ocean between the top and the bottom surface, and it fills the water column and scatters off of things like the fish shoal and goes into the receiving array, and we form the images that way. We also had conventional downward-looking sonar from National Marine Fisheries, which was doing a survey at the same time concurrent with us, and trawl samples to get ground truth. Now, just to give you an idea, here's the Gulf of Maine, so here's the east coast of the United States, and up here's Canada. That's George's Bank, which has historically been a very important fishing area, very rich in life, not super high in diversity, but very high in abundance. But there have been overfishing problems here for quite some time. The yellow tracks that you see are National Marine Fishery survey, and it takes on the order of 2 weeks to conduct this survey. And the spacing between the tracks are on the order of tens of kilometers, so it's very sparsely sampled. And if National Marine Fisheries, for example, is moving through a region and the fish happen to be very dispersed, say in the daytime, and they're not forming a large shoal, well, that's too bad, because they pass through there and they're not going to come back and check again to see what happens later. In our method, what we are able to do is in 75 seconds, about a minute and a half, we're able to see a 100-kilometer diameter region. So in about a minute and a half, we can see an area that's a half to a third the size of the whole National Marine Fisheries survey area. So it's just giving you a different concept of the difference in scales. Now, again, let's look at that area, and we take a zoom here, and this is an example of one instantaneous transmission that we sent out. We found a very, very large shoal of herring. This was on the order of 250 million fish in this shoal. The size of the shoal is, again, tens of kilometers across. It's about the size of Manhattan Island in New York, and imaged from 20 kilometers away. Now, we sent National Marine Fisheries trawl surveys to this location, and just to give you an idea of the vastness of the ocean, it took them 6 hours to get there, and they were nearby our vessel. So there's a very large scales here, and it took them a very long time to get there. And when they got there, they ended up getting far more fish than they usually do in the baskets. In the trawl, they usually get about 2 baskets. Here they got 40 baskets. So they actually never went directly through one of our lines again. One of the other things that we learned is that we had transmitted our radio information, the coordinates of the shoal, over, just ship-to-ship radio, and all the fishing vessels went to the same spot. So we never did that again, and it was actually quite difficult for them to operate in that location. Now, this is an example of some of the interesting biological behavior that we discovered using this new approach in the Gulf of Maine. We were finding during the daytime, we weren't seeing much activity, and this is background level primarily here. And what we discovered was towards sunset, we would see little clusters of fish start to emerge, and within minutes, those would turn into massive shoals. And the shoals would actually propagate outwards, starting from a little cluster. They'd go along the bathymetric contour and just start to grow tens of kilometers in tens of minutes. And so this is now showing about 3 hours difference in time, a relatively well-developed shoal. And this is the concurrent echo sound made by National Marine Fisheries going through the trajectories you see here. And what we found is it's actually a pretty remarkable behavior. This is showing a sequence of images. If we can do it, we'll show a movie too, but sequence of images starting from nothing, then a small cluster, the cluster starts to growing, and eventually, this is about every 10 minutes, you have a very, very large shoal. The nice thing is that we were able to get some echo sounding cutting through as the shoal was forming, and it was interesting that you'd start with these very, very little clusters of fish, apparently some of them bold enough to rise up above the seafloor. It seems they were staying very close to the bottom during the daytime, about 180 meters of water on the northern flank of the bank in deeper water, and only in the cover of darkness would they be bold enough to start to rise up and cluster into a group. I guess too much fear for predators if you start to rise earlier in the day. There's too much light. And it would start in these small little groups. And you see there's a horizontal convergence because there's a conservation of mass. There's no fish mass near the bottom here where the groups are starting to form. They're all clustering up, moving off of the bottom and converging horizontally. And forming the shoal. Later on, once the shoal forms, it becomes very thick and very, very dense. Now, the interesting thing that we found, and we could only do it with our type of system where we're looking at the populations as a function of time at any spatial position, we found that the population actually at a particular spatial position would stay relatively flat and grow very, very gradually. You'd have to plot it on a log scale to see the gradual increase. But then once it reached a critical density, boom, the shoal just started to increase in population very, very rapidly. And in fact, the growth of the shoal would also be very, very rapid in the lateral direction in tens of meters per second. The speed that the fish can actually swim is about an order of magnitude slower than that. So what we were seeing was waves of concentration, the same way you see in a sports stadium when one person stands up, then the next one, the next one, the next one in response. You can send a wave around the sports stadium in a matter of seconds. And if you had to have the individual who started the wave actually walk the same distance, it would take them many, many minutes to do it. So there's order of magnitude difference between the motion of an actual physical particle and the propagation of a wave. And so this is what we were observing here. And one of the nice things is that it actually fit a theory that had been published in the best physics journal in the world, Physics Review Letters, about animal group behavior. And the idea was that if you, a very simple idea based on really one rule and one parameter. And the parameter was that if you have some autonomous creature moving around, it could even be a robot, that was able to sense its environment out to a certain range. And then the rule was that whatever it sensed within its range around it, it would take the average speed of any other similar kind of particle. It would take the average speed of all the particles within its sphere of influence. And what these people had shown was, and the theory was that once a critical density is reached, before the critical density is reached, when the population is small, there was random behavior. But when the critical density is reached, the behavior became uniform and the migration would be in one coherent direction. And it makes sense because the critical density is related to the spheres of perception starting to overlap, and then you have a chain reaction, and that can lead to the kind of waves that I had just been describing. So by our reckoning, this was the first demonstration in the field of that physical theory, and it had been demonstrated with laboratory animals, locusts, but there was the first demonstration in the field. It was on a very, very large scale. And we saw it again and again. This is just another example of another day and another day where we observed this phenomenon. And the purpose of the formation of the shoal, we have hypothesized, is a gathering of the herring to pick individuals of a similar reproductive state to then mass migrate onto the bank to do the spawning in shallow water where they can be picked off much more easily by predators. So the issue is you need to have individuals similar reproductive state so they're not wasting their time in the dangerous predator-infested waters. One of the other points that we'd like to make is that we are transmitting in the range of the swim bladder resonance of the different species. And so you get very strong responses at resonance. You go below resonance, this is around 400 hertz, which is, fifth string on, top string on the guitar, fifth string, it's close to the standard pitch A, 440. An octave up, and this is where we're getting some very strong returns, whereas lower we weren't, and higher we're getting more. The background is the dashed lines in the histogram, and it's staying about the same, but the fish is moving up very strong, and it's a very, very strong resonance. People who know some physics will recognize this is standard harmonic oscillator resonance, and reaching, the theory says, a nice peak. We didn't have data points on the other side, unfortunately, but we're measuring the classic resonance. You can actually characterize the species by the way they resonate, and you can think of the fish swim bladder as like a tuning fork. You hit it at the right frequency, it's going to resonate at that frequency. You hit it at the wrong frequency, you're not going to get such a strong return. Different sized fish have different sized swim bladders, and they're going to have different type of tuning fork. So this is a really optimal frequency range to be doing species classification. And there were a number of interesting points that we can get from this, but truly this is one of the hopes is species classification. It just happened to coincide with the ORS method employing longer range propagation where these types of frequencies are needed to travel long distances in the ocean. Higher frequencies will attenuate more rapidly. One last point, I see the time is out, I just want to make one last point about some of the issues that have been confronted. We've been confronted with this technology. I don't know if people recognize this guy, but he was probably in the news 5 or so years ago. Actually ran for president. He was one of the guys who ran for president against George Bush. And he was the Democratic contender. And he's a senator in the United States. We had 2 big senators that were interested in fisheries issues. And one of them was Senator Stevens, a Republican. He actually died the day before this picture was taken. And this is Senator Kerry from Massachusetts. Senator Stevens was in Alaska. And they were actually very friendly. They were on different sides of the fence, both interested in fisheries issues. They both have come to us asking about this technique. And so this is my colleague, Purnima Ratila from Northeastern University. That's me over here, and this is some congressman. And they wanted to know what this technique could do. And here he is actually sitting, watching some of the view graphs that you saw. And in the back here, you see the thing that drove it, and these are fishermen from Gloucester, which has serious problems with restrictions being imposed on the fishermen, and these are a lot of state representatives. This is the owner of one of the biggest seafood restaurants in the United States, legal seafood, and environmentalists here. And I guess the point I'm trying to make is it's a huge community with a lot of different interests and a lot of different perspectives on it. And you know, the technology is there, and it's something that is part of the debate on how it should be used and what it should be used for. And the fishermen are actually hoping that it will help them understand better idea what the quotas should be and what fish is out there. And one thing we have found is that it's true that we are seeing more fish than the National Marine Fisheries was seeing, by about an order of magnitude, but that doesn't mean that the interpretation of what the regulations should be changed at all, because that was one instantaneous look, and they've been looking over years, and it's really, as everyone knows, it's the trends that are the important issues. So I think I'll stop here.
Thank you.
One last point, if I can make it.
Yes.
I presented the initial view graphs here in 2004 at the University of Concepcion, very raw material.
Yes.
And I got so much enthusiastic response. I mean, I hadn't done any fisheries work before then. And they all told me, well, you should publish in Science, and you should get a patent on it. And wow, I never thought of that. And all those things happened. So thank you.
Yeah, thank you. Thank you for coming. Is there any question? Yes, thank you. Is there any question?